finite or count, but always countable and countably infinite also. Like you don't know how much it will be in the end. Like number of population in entire universe till world end. So we don't know how much it will be, but it is countable in nature. That is why. And then we define this probability of getting exactly that value. Suppose what is the probability of getting, yeah, but here saying is if you define discrete s, that is function of r real space. So there are these r x, sorry, r n z, z plus z minus. These are standard notation of representing numbers. So r is like entire numbers, real number, positive, anything. So Sx everything is actually belongs to R. In that case, yeah, the probability of that will be one, and yeah, this we can skip values. So for discrete, sorry, yeah, discrete event, you will be saying it should be equal to some xi. That is the probability of getting the value of xi. So suppose you want count number of how many times dices have had in twice you turned it or thrice you turned it. This is point probability, meaning that value you know exactly that you are looking for. How many times? Two times in two rows, two throws. You want probability to be uh, exactly two times. So that is why how many times then you when you calculate that is point probability we call them. And what is the idea of probability mass function is actually you are plotting these values for entire xi's. So if you plot them, it will come into some graph, and if you do it as a step function, we call this, it is summation of till xi. So how to explain? Yeah, this is some probability. So x, you can say right left hand side probability mass function. It is saying we see there is x-axis, that is like number, you can say in that example we have, right, how many times we get 1 and 0, sorry, on dices how many times, if you get that example, if you see, I also drawed this example, yeah, number of heads, a number of tails actually. So you know for 0 it will be 0 by 8, because sorry, getting tails, number of tails in 3 experiment, that is 1 by 8 actually. So for 0 value you will actually plot 1 by 8. So how this will come, yeah, let's, we can, yeah, quickly plot also and paint. So what I am saying is for yeah, so what you will be having doing is here you will say it is oh sorry, this is for 0 axis. So maximum you can get 3, right? 3 heads or tails in that example. So we are talking about tail. This is 2 and this is 3. So yeah, this should, I should remember. Oh, eraser. Yeah. So I'm saying, yeah. So 1 by 2 you will, 1 by 8 height of this will be 1 by 8 actually. So I'm meaning 0.125 you will plot. Then what is the problem? How many times you can get one head, one tail? If you check, it will be actually 2 by 8. 1, 2, 3. Actually 3 by 8. 3 chance. Right? Either in the last you will get tails, in the mid, or in the starting itself. Then this height will be 3 times of that. That is 3 by 8 kind of. Again, you will do the plot for getting 2 times. So getting 2 times is also 3 by 8. So you will plot the same height 3 by 8. And getting 3 heads uh, in how many times? That is 1 time. So the probability will be 1 by 8. So this is PDF actually. We say is like we check all the possibilities and we plot them, how it looks like. So we say not PDF also, but PMF actually for discretes. Right. Are you understanding what we are saying? We just plot all the values, all the probabilities for each of the values, whatever possibilities we have.
Yes, Rishi. I mean, with that graph example, I was able to understand.
Okay. In CDF, what we say, yeah, CDF, PMF. So CDF, what we do is cumulative actually. We just sum it over. So for CDF, if you draw for this one, it will be similar, but oh, sorry, 1, 2, 0, 1, 2, and 3. So see, in this case, if you are looking for less than number of zero tails, it will be always zero. Probability will be because you are not going to get any, meaning less than zero is zero actually. So this will be something like this. But after zero till one, you will get 1 by 8 probability. That is 0.125. But what we do is cumulative. Now you are checking like either one number of meaning getting 1 times tail or 2 times tail. That will be actually sum over it. So we should actually 0.125 plus 3 by 8 is nothing but 3 times of that 375. 0.375, and then it will actually become half. So next line should be at zero point 0.5 actually. Then you are actually summing it over. Now the last line, uh, yeah, in this actually you are not including one. In zero is included, and similarly you will get one more line near to one, that is 0.875, and last line will be actually at one, exactly one. So in this way we draw a CDF, and what we say is like the distribution will look like something like this. We will connect this and saying now here itself it should go into that this axis as y1 equals to 1 actually. In the y-axis control set, we had we are actually having what to say, this axis, yeah, this is nothing but probability equals to 1, yeah, this value. So these are actually representation of defining these things and trying to visualize how probability will look like. This is probability equals to 1 and this will be probability equals to zero point 0.5, exactly half of it come into picture. Yeah. So
Rishi, for me, the CMF is not understood, the cumulative. Why we do
cumulative
this?
is, yeah,
Optically,
you are saying till 0 it will be 0. 0 to 1 meaning not exactly 0 to 1. Till getting 0 meaning uh, yeah, till getting 1 you will be, oh okay, yeah, correct. I should be it. Yeah, correct. Zero number of tails is nothing but there is one by one chance, right? All head are there. So that is 1 by 8 actually. So we are saying 0 and not including 1 actually. How this PMF will come right here actually. If you see this graph, also we are saying till x1 will be 0, x1 onward till x2 actually, but x2 is not included. And in this actually you are saying either less than equals to xi and sum over all the probability. That is how we are defining this function of x actually.
That is.
So what we are doing to get the CDF, this function fx of 1 in the sense how many times we are getting this f of 1 is nothing but f of 0, and we say function of 0 plus f of 1 actually. So what we are saying 1, right? So in this case you will actually sum over 1 by 8. This is 1 by 8 actually. Getting this one, if you remember here, 1 by 8 in this
Hmm.
exercise, 1 by 8, and the other one is plus. Actually, I should write somewhere else. Yeah, so otherwise, again 1b in this case, suppose if I check. Yeah, so here also. So it is like 1 by 8 getting the probability of 0 times tails and get one more. So this line is actually 4 by 8, and that's why it is the second line is at this place, zero point 0.5. When you calculate again f of 2, then actually here it will come this value. So this will be actually nothing but f of 0. F of 0 is nothing but probability of getting. Oh, sorry, it should be not f of 0. It should be p actually, p of I and all. I should be saying this as a p. Probability of getting 0, probability of getting 1. So we are summing it actually. So probability of getting 0 times tails, probability of getting 1 time tails, and probability of getting 2 times tail. So next line will be actually this. Then if you check, it will come 7 by 8. So that is why 7 by 8 when we plot, we will getting here actually this line. Uh, yeah. Oh, yeah, I should be, yeah, leveling by some other lines. Yeah. This is probability of 1 by this f of 2 actually, and highlighted by red actually. So in the last one, you are actually plotting f of 3, that is actually probability of getting 0, 1, 2, and 3. So it will automatically comes as equal to 1 actually.
8 by
So
8. Does it?
yeah, 8 by 8, nothing but yeah, 1 by 8. So you can say like this stacks. Here you are saying just clubbing at the here point and just drawing into different format only.
But which is best to use, like the PMF or CMF, or which for which
CDF, yeah.
use
So
is it?
generally CDF is used, and CDF for standard actually. So if you want to get some probability of 2 only, so what you will say, to get probability of 2, you can actually minus f of 2 minus f of 1, just previous one, then you will get f of probability of 2. So there are some functions or some, you can say, formulas they will define. Based on those formulas, if you remember, or you can understand them, and quite easy to get these things. So in the end, CDF is cumulative actually, right? You are looking at cumulative sum. So getting, what is the probability of getting x1? Then if you plotting for x2, you are actually looking for x1 also and x2. When you're plotting for x4, you are saying cumulative.
Conclusive.
Yeah,
Okay.
x1, x2, x3, x4. So this, we define these graphs. Quite importance actually they have. But this in discrete, right, there are two type or three types of distribution, that is uniform, triangular, and some other will be there. But in this one, continuous, that day we also discussed like lot of distributions are there. In continuous, they comes with different types of saves, and then there actually we required. And now the same formulas which we remember, p of a into p of b, we were writing, right? Independent event. So suppose getting, what is the probability of you getting some 100% marks in the exam maths, and your brother or sister getting exam, they are independent to each other. Similarly, you can say number of getting tails in one, uh, you can say one event, and the what is the probability of drawing ace in the second event. So they both are independent to each other because you are playing two different game actually. So that is also a thing. Now we actually calculate expectation. So expectation value, this actually mostly used in like, yeah, what to say, only property of uh, probability only. What we did is nothing. One extra thing we did in, if you remember, we just summing over this PIs, right? Summing over PIs.
Yeah.
Yes, probability of getting xi's, and xi is how you are defining a number of tails. Right now, take that example. What we will do is, now we will actually multiply this with x also. It is like getting the expected mean, like how much value I will get if I do this maths on this. Actually, this is mathematical term, but expected mean is like, you can say if you do some calculation, it will say like on average, this experiment will give you this value. So probability into excise, excise is the count, right? If you remember, zero into, so how we calculate this? I should, yeah, give this example. What you should do, zero xi into their probability plus 1 into their probability, 2 into their probability, 3 into this probability. So that value we call it xi, sorry, expected mean. That is represented by x of e of x actually. So e of x or mu of x also. This is also have quite significant. So they have some property. If like if you multiply them, you want to add two of the random variable, it will be sum. Sorry, add them. It will be similar to getting the expectation this. And independents are there. Just multiply their expectation. And and similarly, we calculate variance also. So remember how variance is nothing but, you remember standard deviation.
Yes, Rishi.
Yeah, so there we calculate sigma square, right? That is only the variance. So what we are doing, x minus their mean actually, and their square, and taking again expectation. Then this formula is quite useful, they say, useful formula to get the expectation, sorry, variance. So e of x square minus e of inside x square actually. So first you should calculate the expectation of x and take the formula, take the square, and other one is get the square's expectation and calculate the. So yeah, these are some, I think, yeah, that's all. Similarly, we have covariance also. I think it depends on two variables. We are calculating on two of the random variables, and same formula is there kind of, e of xy minus e of x and e of y. And this value actually says how they are related or how they are varies actually if we have some two event. Yeah, I'm skipping this. They have some significance in, like, you can say you can relate with real life examples, but generally, yeah, quite not useful much. But yeah, these are like underlying formulas between some other derivations and all. So similarly, we use this standard deviation. Standard deviation is somehow they are related to square root of variance. And if you remember just now we talked variance how we calculate here only e of x minus x square, that is mu. This piece is e of x is mu. So you are calculating actually getting the mean, taking the square and their expectation, and that is actually the and coefficient of variation, and then kth mean. Kth moment you can ignore as of now. So mu of 2, mu of 3, what they say, you can just square it, cube it kind of thing, and like that, yeah.
Rishi, in our data, like if we get a data from the user, where the statistics and probability will be applied, because directly we are into the what is this pandas library, we will try to do our work, right, and then we'll do a visualization. So here, this mathematics and probability at which phase in your screenshot you had shared, right? It is the first point, but
So it's, yeah, standard deviation, what I will say is like standard deviation you will definitely get somewhere, but
that is
sometimes someone asks you to calculate standard deviation on the data. You should be calculating based on some formula, and those formulas actually already coded for you. Just you will just call them and use it there itself. Yeah.
so
So
for that in pandas we have like something dot info or something is there. If we give that, it automatically calculates and give the data, right, on
correct,
mean,
correct.
median, everything.
Yeah, you don't have to much worry about this. It is like how we are calculating, we just aware of it. Yeah.
Okay, okay.
And in probability, yeah, there are only maths only. Then they are main thing is knowing this type of distribution. So before going into that, yeah, I just revisiting what all they had in this slide. And we call this as a one distribution, like sorry, one set of random variables are IID, that is independent identical distributed. Like they all are having same mean, same variance. So how you will denote their means? So average will be nothing but this, and the mean is mu only. It will be same actually expected value, and the variance will be sigma square by n, because there are n number of random variables, and we will calculate their this d. They are representing that variance. This is sorry, this is standard deviation, this is variance, and this is expected value. So this is how we calculate. So they are writing right then proof. So actually based on this formula, using the previous formula, you will calculate and get this. So they are just writing, yeah, this should be the final case. And what will happen when you say this law of large number, and with probability 1, so as this number n, right, n grows as so large. So what we are concluding with this theorem is, as n grows infinite, your mean of this will be actually exactly mean of mu. So they both means will be same actually. That is the idea. Yeah, this mu will be same for all the probability with probability 1. So the idea is like if your in n is increasing slowly by slowly, and the with 100% probability, the mean of this all the random variables will be same as the mu actually. See what they are saying, xi has also mean mu and xn has also mean mu. and their means will be nothing but 100% chance that it will be mu only. So it's quite obvious, right? Average of 10 student in class A is 10. Suppose height is 150 meters, 150 centimeter. In the next class also it is 150 only. Next class also 150. And then if you take the average of this average mean, it will be also 150 only. So that is only the formula or this law of large numbers say. And now we have this two distribution. So Bernoulli was, if you remember, they I said there is when there is probability only of getting two outcome. That type of experiment we call them as a Bernoulli, and where you can say P is the probability of success and 1 minus P is the probability of failure. So classic example is toss, cause coin tossing. So their probability of success and failure will be zero point 0.5 and zero point 0.5. When you have two outcome, you only call them as a Bernoulli distributed event. So yeah, then someone can they who are actually into too much statistics or this pure probability, they can ask like what type of experiment this is.
It
If
is
you
like
remember,
based on scenario they gave and which distribution should be
yeah,
used.
yeah. So
Okay.
yeah, this is one way, and this is only one toss, right? Symbol one random variable. So again, binomial I told. Like if you are doing the same Bernoulli experiment multiple times, right? Independent event, simple experiment of Bernoulli types many times. So then this formula is converted into, suppose you are tossing the coin 5 times. Now I will ask what is the probability of getting success in any single event, or probability of getting 3 times head out of 5. How you will calculate? Then you can use this formula actually. 5c of n, you know this 5c of n. Sorry, nc5, nci. This bracket it is written. This one. Hello?
Yes, Rishinu, I was trying to read that N of I box.
Yeah, the C, how we call this NCI actually.
NC.
The permutation and combination class, if you had combination versus permutation, they have this formulas, right? Yeah, this one.
Okay.
NCR, this is how we represent, and n factorial divided by r factorial r, n minus r factorial. Factorial, if you know, it is nothing but product of till that time. And NPR also we define n factorial upon n minus r factorial. So permutation is nothing but choice of r things out of n things without repetition. Then these number of permutation you are actually. Combination is choosing without repetition where order does not matter. Then this will come. This formulas come.
Yeah,
So
this formula makes.
maybe you can recall again. In case if you have I still doubt, you can ask. Yeah, we go back to that formula. Oh, sorry. Yeah, here. So, and yeah, here they are writing n factorial is nothing but product of n minus 1 and 2 till 1, and how we are defining. So this is how you will calculate, saying that I asked you are doing the n is equals to 5, 5 times tossing your experiment. I am asking 3 times how much, what is the probability 3 times you will get head, and then you will write probability of getting head in one event, getting tails in one event. 1 minus p, that is head only, and minus I. This formula will give you probability of getting 3 times tail in 5 experiment when you put n equals to 5. Similarly, you can calculate mean also, mean and this variance, but these are not relevant. Mainly people will ask point probability, that is the formula. 3 times, 4 times, or 2 times, yeah,
Okay.
out of 5. Similarly, we define this geometric distribution. Number of success until first failure is an independent series of simple remote. So what they are saying, uh, what is the probability you will continuously get the head, and once you get the tail, it is failed event. We call it first failure. Suppose you are defining success as a head and getting tails as a failure. So I am saying, what is the probability I will toss my coin 5 times? What is the probability I will get sixth times tails? So that probability actually we calculate using this formula, P of I 1 minus P of I. So it's straightforward. First 5 event, suppose I am looking, first 5 event is nothing but probability of getting success, right? So it will be zero point 0.5 in the first also, next also zero point 0.5, zero point 0.5, zero point 0.5, zero point 0.5. And in the end, when you are getting the sixth one is a failure event, right? Tails. So 1 minus P, then that is actually the probability of getting sixth time tails. It's quite intuitive also. You can just think through it. So someone asked like 1,000 time I want to try this, and on the 1,001st time I should get the tails, but first 1,000 times I should get the head. So this is how we define this geometric. So it is like getting the first failure. So when this type of questions actually comes is, suppose you are in bulb manufacturing company, so they actually ask this question. Such question is comes into there is like, I am doing this testing, right? All the bulbs will be manufactured correct, right? Some will be, very less will be defective. So the question will come like, 1,001st time I should get the failure bulb, what is the probability? Because probability of all the bulbs are 100%, like 99% chances it will be not defective, right? Some can be defective. Then actually these geometric distribution come into picture to calculate what is the probability of 500 times. First 500 bulbs will be you what say not defective, and the next one will be defective. So such questions comes there, kind of one geometric distribution, getting the first failure. So that is the idea. All the events are actually checking one bulb is independent to the next bulb. That is why it is independent series also, and each bulb is Bernoulli type also. You can see the probability of getting first bulb failure or success is not dependent on the next one, and you can calculate their probability of getting this bulb as a failure or defective or not defective. So this is how we calculate these. Yeah, they have some standard formulas you can ignore. And this actually has geometric distribution has some quite good property, that is we call as memoryless. When we say memoryless, you can say is uh, how to explain this. It is like today's weather is not dependent on tomorrow's weather. So if you want to calculate the tomorrow's weather forecast, you can ignore the today's forecast actually. So that is how you can say is like, today is I and tomorrow is J, or you can call this as a geometric also. Fifth. So suppose fifth event is failure. I want to check is the ninth event is also failure. So if you're given that fifth one was failure, and the ninth one you are checking is it going to be fail or not. So it is independent of that actually. So it will come directly. You can write it should be greater than 9 and all. So probability of failure of ninth is same as independent of probability of getting the fifth one fail actually. Condition on fifth actually. So something like that. It has one probability, or you can say one property. When you use such, yeah, I think examples while solving problems. Yeah, actually, I thought of we can do it. Similarly, this is minimum and maximum we can calculate. Yeah, I'm skipping this. Yeah, one more comes into this poisons. Uh, Poison is generalization of binomial distribution. Actually, here the n was finite in number. Now n is actually infinite is number. That's all binomial. So when you define this as a infinite, n is going till infinite. Yeah, then that case we can say, and that kind of little complex formula we have to calculate. Here exponential will come into picture. So one example of probability is like number of queue in at ATM can be a number of people. So when you are saying that is infinite, right? How many numbers of people can come is infinite, and they are countable also, and probability in that case will go zero, because you can say sorry, infinite number of people will come, the probability is zero, right? Never will happen. Like all of the people's world's population is queued at one uh, ATM. So
Rishi, this was like last time you mentioned, right? This poison and Bernoulli is important, right?
hmm, they
The,
are actually, yeah, you can say, let's talk about this example how they are explaining. uh what they saying, assume that 200 subscriber are connected to local exchange. Each subscriber's characteristics tariff is zero point zero 0.01 erlang. I don't know why. Subscriber behave independently. Then number of active calls is actually distributed binomially, 200, and the probability is zero point zero 0.01. Corresponding to Poisson approximation, you can say Poisson of 2. You can just multiply these two numbers. So you will get Poisson of 2. So yeah, NP equals to A. So A is here. So NP. So Poisson of 2. Then actually you can check the table. So what is right? These binomials tables and Poisson tables are present online actually. So previously how we used to calculate, now in the calculator you can write Poisson of 2. These values will come based on the whatever x you want, right? Here actually using this formula, IU will be entering, right? But these formulas were actually in the tabular form. Have you seen logarithm table? We used to get that table, log table.
yes, Rishi.
Yeah, so that time during previously, actually, you used to check these. Also, they used to provide this binomial table or normal table. So you don't have calculator. Actually, you use those tables to get these values. So you can see Both are quite exact approximation of each other. These values are not too much different. So idea is if you increase this 200 to 300, this value will be more closer actually. That is why they say like Poisson is good approximation for binomials. So they will not provide binomial table, maybe they will provide Poisson table, quite useful. And instead of calculating binomial values, you can write this Poisson's value. That is fine. I skip this here. They have many properties, and yeah, they are not much useful to us. Yeah. Let's go to the continuous. Similarly, if you remember, I was talking about summation, right? To calculate C of x, CDF,
Yes.
continuous array. Yeah. In this case, we also calculate again CDF, that probability, then PDF actually. Small f is PDF, getting exactly value of some x, small x. Is f of a small x, but getting less than equals to x, like just now we talked, right? Getting till 3 or till 2, it is sum over till this 2. So here also it will getting sum over minus infinity to x. If you know, integration is like summation over all the x till x minus infinity to x. This we call at CDF, and the f of x is PDF. That's all. I think when you say same thing, you can do plotting of PDF versus CDF. It will come like this. In
No,
here,
there
it
was
is,
this is two different thing, I guess. That was having a mass, probability mass. Probability mass and density goes same.
yeah, correct. They are kind of same, but in that one, if you remember, you have to draw bars. They
Okay.
are discrete, right? How you will say discrete? You have to draw bars. CDFs are continuous, this one, but as it is exercise are discrete, right? You have to mention something like this step function. It will be always like that for discrete ones. But in this one, continuous one, these will be little discrete PDF, but their cumulative distributed function, they will be always continuous in nature, meaning these lines will be always joined. And in this, you have to define till 0 to 1 also, and minus infinity also. Similarly, if you remember, we multiplied by x and calculated the expectation value. You can calculate the expected value for this continuous one also. Now they are also like skipping. Use 21 to calculate other properties. Use 21 to 24 for variance, covariance, and different other properties of this distribution also. Actually, only maths will change based on continuous. You instead of using sigma, you have to use this integration because it's continuous, and that's all. Yeah. Let's talk. So we call this as a uniform distribution, one function. It is like, yeah, casting a dice, where probability of getting each dice, right, in dice, getting number 1, 2, 3 is nothing but 1 by 6 always. That type
Yeah.
of distribution we call it as a continuous distribution. Also, Wait a second. Yeah, but that is also discrete in nature, right? Yeah, that is not uniform actually. But yeah, uniform distribution example will be. Let me also check. Yeah, okay, okay. We can call them as a discrete. And similarly, getting a card of deck is also uniformly distributed because their likelihood of getting heart, club, diamond, spade, that is also same. That is nothing but 1 by 4, 1 by 4 for each of the value. So you can call those as a uniformly. Similarly, we have exponential. It's a continuous counterpart of geometric. It's a similar thing. If you convert that geometric into continuous nature, it will come as exponential distribution. In exponentially distribution, that is kind of this is also kind of useful in nature. We should actually remember this formula. Yeah, we should know this lambda. So lambda will be always given that probability of or not. Yeah. Oh, okay. Yeah, actually, one distribution quite useful is like we call this as a long distance business telephones calls, like amount of time it will get the next call or something like that. You can say as a distribution, or they are exponentially distributed because mm, how to say, because yeah, that is also. But yeah, those examples are actually exponentially distributed. You will give some, so they will say at this lambda rate, meaning after 5 minutes or 6 minutes, you are getting one call on average. But because their probability is like this call will go 2 minutes or 3 minutes, you are not sure because those calls will how long they will last, those depends on exponential function actually. They will exponentially in nature. And similarly, one more example is like amount of time until an earthquake occurs is also exponential decreases because as time grows, your probability of getting that event will reduce actually. Yeah, this one also have same memory less property. Today is getting the assuming, yeah, this one assume the call holding time is exponentially distributed. Consider that a call has already lasted x minute. So it will again go for h minute or not. It is independent of x minute, previous x minutes, right? So you can say you talked with your mom with 5 minutes. Now you are going to talk for 7 minutes. Independent, right? It is not have any information. Either you talked about 5 minutes or not. So that is how we call this as a
Memory.
those, yeah, time actually. It's a time distribution. Most of this thing will have some time component. When you have something with time, you should think about exponential distribution. Similarly, you can calculate these min, max, and yeah, they have some properties similarly. Now, the very important comes is standard deviation. And when we say they are mean with 0 and variance of 1, then we call this as a standard deviation, and they have special formula actually. PDFs has this formula. and CDF have. So if you know PDF, then you can calculate CDF. Remember, normal are always distributed with mean 0, variance 1. When we say Gaussian, Gaussian is distributed with mu sigma square, but they are actually somehow related with normal. You have to convert it and now later on calculate this. So there are many for properties. Yeah, this one. This has very significant application in statistics. What this theorem says is, as you increase the value of number n, it will actually go to this. It will be ID, meaning independent, identically distributed with normal 0 and 1, and it follows. Then x and you can calculate based on this formula. These two I escape, but yeah, CLT we can talk. Central limit theorem. See. So one example yesterday also I was reading about this is yeah, actually yes, I should check this. Yeah, so what we are saying is, suppose you have two more concept I will bring here. One is population, and another one is this sample. So population and sample, if you sample is only a small part of population, and population you can say, suppose you are trying to predict the height of entire you want to some do statistics on entire population, that is India's population. So it is impossible, right? You are not going to calculate the height of entire India one by one. What you can do is you can take some sample and trying to some make some assumption, yeah, based on population, is it same or not. So this is where this population and sampling concept comes. And assuming you are doing this truly random sampling, then actually, so then actually your theorem will work actually. So sample will actually represent your population. Otherwise, if it is not random in sampling is done, then you may be biased, you having some bias towards. So how, suppose you are doing this experiment trying to get the mean average of height of India's population. How you will try is like, you should randomly pick any number of 100 number or 1000 people and take their average. Get that average, you will say, yeah, this average actually represent my this one population's average. So, but that is like, yeah, that is also very not sure is it correct or not. So there are other way. What you can do is, instead of taking the 1000 people, what we will do is we will actually do. So suppose you find this. Suppose we have a population distribution like this. Actually, the heights are, or this is what we actually did is. Uh, Suppose, yeah, estimating height is, and we found, yeah, these many peoples are having zero height, because some peoples are very higher in nature and all height. Why is this distribution will comes like this? So now what we are doing is we actually call one more thing is sampling distribution. what is the idea is like you are now going to sample 100 people in the group of three people you will take and trying to calculate their height and try to free check and point. Yeah, then you will try to plot them. Actually mean distribution with n equals to 8 3 sorry, three people you took on out of 1,000. So suppose you have only 1,000 people, but you are actually taking the group of three, giving their mean and plotting. Now again you will do what? Take one more sample of three people randomly. So means will come like this. The height, why I don't know why they are talking about height here, but that is not height. You can say age. You can say age of the person. 5 age 20 41 then 60 6 70 whatever. Based on that you will try to plot them. So if you try to plot this sampling distribution as n increases, this is for group of 3 people. When you increase by group of 10 people, it will come like this distribution. When your n increases 30, it will be something like this. So this plot says as your n increases, meaning sample of this sampling distribution size, or not size, actually the size of the sample, this distribution will actually uh, become closer to that sorry, normal distribution. So this idea is actually quite you can say it's not intuitive in nature, but one example can be, suppose you are doing head or tail, right, in a coin. So you did toss that 100 times. So obviously in 100 times there is probability, meaning you get 40 times tail and 60 time head, right? What will happen if you increase this 100 to 200? How many heads and tails you will expected to get, kind of, just a number? Hello?
It will be the same as the previous one, right? If we increase the number on two values like
Yeah.
for head and tail.
So you can say now if you are saying 200 toss, now the probability is like maybe 110 are head, now 90 are tails, right? As you increase this, now 500 tosses you did. So 100, now 110 will can become 250 or 251, and tails will be 259 49. So in the eventually what will happen, right? This will 50 numbers of head will come and 50 numbers of tail is as your number of experiment increases. So it will actually replicate the exact probability of getting this head and tails as your number of experiments increases. So similar way, this central limit theorem also says as your numbers of in this size increases in the sampling distribution, this sample distribution will actually close to normal distribution. That is the idea. And based on that, there are like many problems they will come and solve.
Actually, I think your screen is stopped for me.
Yeah, yeah, I stopped actually
Okay, okay.
because we were only talking, right? Yeah, there was nothing to share. So I just share again. So I am saying then this sampling distribution will look like similar to the normal distribution. That is the blue one. Mu with 0 and sigma with 1. Okay, yeah, mu with 0 and sigma with 1. Red one. Correct. Sigma square with red one. So that is the central limit theorem. So they have quite. So what eventually is, instead of you doing trying to predict the population parameters, what we do is we do experiment, multiple types of experiment, trying to find some characteristics of this population. That is the idea. This is one thing, and now I think it has some other topics also. We talked about explaining this Data types and various, this we can take later. Data representation. Yeah, this we can also. We talked CLT, that is fine. And now there is like, yeah, point estimation and confidence margin. This I wanted to cover. When we are estimating some value, exactly point value, what we say is like point estimation. Exactly some. So this point estimation mostly like you want to estimate what is the height, average height of some group. So you suggest one value only. When you are approximating with one value, you will say this is point 0.1. By this example, yeah, you can see. So we are saying like, yeah, this is point estimation, and probability will be like single point. You are saying average of height of 60, or marks is actually something like that. Point estimation. Similarly, what we do is interval estimation. So interval estimation is like your average height will be within 155 to 160. So that is like interval. You are giving some min and max. And now you will say confident is interval is like what is the probability, like it is going to fall between that. So when you call something like that, then you are coming up with this. So point estimation plus minus, you will say, yeah, 167 is the height, and there is some margin of error. You will add into it and subtract into it. Based on that, you will say, this is my uh, interval of estimation. I am surely that 99% or 95% chance your average will be between these two days, from x bar to minus something, y bar to minus something. This is how we define like point and interval estimation, or that is also known as, what was the word they were using, confidence margin and all. Yeah, so same thing is there. Hypothesis testing, there actually comes two thing. Hypothesis is actually what is like, you say this data is one hypothesis, small hypothesis. You can say one, this data whatever I get from the client is exponentially distributed. This is your hypothesis. You are trying to prove this data is exponentially distributed. Now you will do some testing on it, trying to calculate their lambda and everything, whatever properties they have. You will do t-testing or some testing based on the data itself and what type of distribution you want to try to fit. And there will come a one probability of p value we calculate, which says like probability of rejecting this hypothesis. And if this p, you decide actually in this p is like it should be lesser than 0.5, 0.05, 5%, less than 5%, I will reject null hypothesis. There are two types of hypothesis, that is I think levels of hypothesis testing he's talking about. So there are two hypotheses we say. Either the distribution is sorry, that data is distributed exponentially, one hypothesis. Other hypothesis, it is not. That's all. So when we say we are rejecting the null hypothesis, it means that the data can be or cannot be exponentially distributed. We are not sure. But if we are accepting that null hypothesis, this means